Hello friends, welcome to YouTube channel Electronics. In this video, we will learn about transistor. Transistor is one of the most important device ever to be invented. Believe it or not, your computer and smartphone have billions of transistors in it. The heart of a smartphone is its processor, and this processor have nearly 12 billion transistors. The name transistor comes from merger of two words, transfer and resistor. So it performs some sort of transfer of resistance. Transistors comes in many shapes and sizes. It is a three-terminal semiconductor device which can act as a conductor or insulator based on the applied input signal. Due to this property, transistors can act like a switch with no moving parts, and they can amplify a weak signal. In fact, amplification is the basic function of a transistor. There are two main types of transistors, field effect transistor and bipolar junction transistor. We will focus on BJT in this video. Transistors are made of semiconductors such as silicon. Semiconductors, for example, silicon atom have 4 valence electrons. So each silicon atom is bonded with 4 neighboring silicon atoms. These bondings are known as covalent bonds. The process of adding impurities to a semiconductor is known as doping. Doping improves conductivity of semiconductors. If silicon is doped with pentavalent impurities, it creates free electrons. This is known as N-type doping. Similarly, if silicon is doped with trivalent impurities, it creates holes. This is known as P-type doping. So, depending on the kind of doping, semiconductors becomes either P-type or N-type. When both P-type and N-type semiconductors are joined together, it is known as PN junction. The charge transfer at the junction is known as diffusion. This is how diodes are made. They consist of PN junction. If you join three semiconductor materials, either by sandwiching a P-type material between two N-type materials or by sandwiching a N-type material between two P-type materials, a transistor can be formed. The section on one side termed as emitter, middle section called as base, and the other section termed as collector. There are two types of transistors. First one, NPN transistor. Two N-type semiconductors are separated by a P-type semiconductor. NPN transistors are represented with this symbol. The arrowhead is always at the emitter, which indicates the direction of conventional current flow. The term bipolar indicates that both electrons and holes contributes in the flow of current. The other type of transistor is PNP transistor. Two P-type semiconductors separated by a N-type semiconductor. PNP transistors represented with this symbol. If you want to understand how a transistor works, we have to get a clear idea of a PN junction diode. If we apply a forward bias across a PN junction, as soon as input voltage is greater than 0.6 volts, electrons in N region and holes in P region push it towards each other. Due to this, potential barrier gets eliminated and there is high current flow in the PN junction. If we apply reverse bias across a PN junction, holes will get attracted towards negative terminal and electrons will get attracted towards positive terminal of the supply. So the potential barrier gets increased and there will be no current flow in the PN junction. A transistor is nothing but two PN junctions with two potential barriers, emitter base PN junction and base collector PN junction, and it appears as two back-to-back diodes connected in series. But it won't work like that because there is no interaction between these two PN junctions. If we observe the internal construction of BJT, the base is much thinner than other regions, while collector is wider than both. The emitter is heavily doped so that it can inject charge carriers into the base. The base is lightly doped. It passes most of the emitter injected charge carriers to the collector. The collector is moderately doped. It collects the electrons injected from emitter. Transistor is two PN junctions connected back to back. So whichever way you connected the power source, one diode will always be reverse biased and blocks the electric flow. This means the transistor is in off state. Now let's take a NPN transistor and apply forward bias between emitter and base. So this is just a forward bias diode. As we know, emitter is heavily doped. Base is very lightly doped. Therefore, high number of electrons will be emitted from an region, but few electrons less than 5% will combine with the holes, and some electrons will attracted towards positive terminal of the supply, giving rise to the base emitter current. There are more than 95% of electrons are able to flow right through the base region into the collector region. As we know, collector is moderately doped. If we apply a reverse voltage to the collector region, then these collected electrons will attracted by the positive potential constitutes collector current. Collector current is much higher than base current. The ratio between the collector current and the base current is called gain of the transistor, denoted by the Greek symbol beta. So let's say the voltage at the emitter is VE, the voltage at the base is VB, and the voltage at the collector is VC. And to forward bias this base emitter junction, the voltage of the base should be greater than the emitter. And similarly, to reverse bias this collector base junction, the voltage at the collector should be greater than the base. That means to flow current through the BJT, collector voltage should be greater than base voltage, and the base voltage should be greater than emitter voltage. This is called biasing of a BJT. It is essential to apply voltages of correct polarity across two junctions of a BJT to work it in active region. In active region, BJT works as an amplifier. If we reverse the voltage across emitter and base junction, now both junctions are reverse biased. Then the electrons in the emitter region will attracted towards positive potential of the input supply. Due to this, the width of the depletion region between emitter and base increases. So the emitter does not supply the charge carriers to the base and collector. Hence there is no current flow in the BJT. The BJT just acts as an open switch. This is called cutoff region of the BJT. If we apply forward bias across both junctions of BJT, here base voltage VB is greater than emitter voltage and collector voltage. Now the electrons will get injected from both collector and emitter. Due to this, the potential barriers will get eliminated. Electrons will start moving freely in the BJT, and BJT just act like a closed switch. This is called saturation region of BJT. If we reverse the voltages across both the junctions of BJT, now emitter base junction is reverse biased and base collector junction is forward biased. This is just opposite biasing of active region. Now emitter voltage VE is greater than base voltage VB, and base voltage VB is greater than collector voltage VC. This region of operation is known as reverse active region of BJT. in reverse active region, the electrons will get supplied from collector and collected from emitter. Due to this, the gain provided by the BJT is very less. So, this region of operation is usually avoided. Similarly, if we talk about PNP transistor, then in case of active region, emitter voltage must be greater than base voltage and base voltage must be greater than collector voltage. Hence, PNP transistor active region biasing voltages should be like this. Emitter voltage should be greater than base voltage and collector voltage. PNP transistor can also be operated in different regions by changing its biasing conditions. So, to use BJT for amplification, it must be operated in active region, and to use BJT as a switch, it must operated in cutoff and saturation region. Now, whenever the BJT is used as an amplifier, then there are three different ways to configure it in active region. First one, common emitter configuration. Emitter terminal is common for biasing. So the input signal is applied between base and emitter and output is measured between collector and emitter terminal of the BJT. Similarly, in case of common base configuration, base terminal is common for applying input and measuring output. Likewise, in common collector configuration, the collector terminal is common for applying input and measuring output. Each configuration has its own advantages and disadvantages. We will discuss them in upcoming videos. BJT can be used as a switch. It acts as a closed switch in saturation region and acts as an open switch in cutoff region. Let's discuss switching application of BJT with one simple example. We know that if we connect a light bulb to a battery, it will illuminate. We can place a switch into the circuit and make the light on off by interrupting the power supply. But this requires a human to manually control the switch. We can automate this circuit by replacing the switch with a BJT. Now this BJT is blocking the current flow because of the potential barriers. So the light is off. But if we provide a small voltage to the base terminal, the potential barriers will get eliminated and BJT will start allowing the current flow through it. So the light turns on. If we insert a temperature sensor like this, then we can automate the control of the light bulb. Typically, we need to apply 0.6 volt to 0.7 volt to the base terminal for the transistor to turn on. BJT can be used as an inverter to change the logic levels of the input signal. Let's take a NPN transistor, connect emitter to 0 potential and collector to the positive supply through a resistor. Now apply a input pulse to the base terminal. We measure output between emitter and collector terminals of the BJT. When the input pulse level is less than 0.6 volts, because of the low level at the base of the transistor, potential barriers will not get eliminated. So it acts as an open switch. So the entire VCC will appear at the output. Whenever the input pulse level crosses the 0.6 volts, because of the high level at the base of the transistor, the potential barriers will get eliminated in the transistor. So it acts as a closed switch. Hence we will get 0 output across the BJT. This will repeat for the next pulse levels. If we observe the timing of the input and output pulse levels, whenever the input is low, output is high, and whenever the input is high, output is low. This ability of a BJT to invert the input signal logic levels at the output makes it a very useful component in digital applications. Apart from this, BJT can be used as an amplifier in analog applications. Let's do an experiment with this simple NPN transistor circuit. Just take a variable DC power supply and connect positive to the base and negative to the emitter. When the supply voltage to the base pin is 0.5 volts, the transistor is off. So the lamp is also off. If we increase the supply to 0.6 volts, the transistor is on, but not fully. The lamp glows dim because the BJT is not allowing the full current to flow through the circuit. If we increase supply to 0.7 volts, the lamp glows brighter because the transistor allowing almost the full current to flow through it. And at 0.8 volts, the lamp is at full brightness. The transistor is fully allowing the current. So what is happening here is we are using a small voltage and current to control a larger voltage and current. We saw that a small change to the voltage on the base pin causes large change on the main circuit. Therefore, if we apply an input signal to the base pin, the transistor acts as an amplifier. Let's see how this NPN transistor circuit amplifies input signal. We have applied bias voltage to BJT. So the forward bias is maintained regardless polarity of the input signal. We will apply input signal at base and will measure output at collector terminal across the 5 kilo ohm resistor RL. Let's apply 0.1 volt positive sine wave at the input. Suppose it produces 1 milliampere base current. Due to this, the forward bias across the emitter base junction is increased. Therefore, more electrons will flow from emitter to collector via base. This obviously produces a change in collector current, which would also be 1 milliampere. Here base current is 1 milliampere. Collector current is also 1 milliampere. So the load resistance 5 kilo ohm placed in the collector would produce a voltage of 5 kilo ohm multiplied with 1 milliampere. That gives 5 volts at the output. Hence, it is observed that 0.1 volts input signal will be amplified to 5 volts in the output. This means voltage level of the signal is amplified. However, during negative off cycle of the input signal, the forward bias across the emitter base junction is decreased. So, the base current will decrease to minus 1 milliampere. Therefore, collector current also decreases. This results in decreased output voltage in opposite direction. This is how we will get an amplified output across the load resistor. We can design a basic audio amplifier circuit by connecting a microphone on the base terminal, which feeds varying input signal. We will get an amplified output from the speaker, which is connected to the collector terminal through a transformer. The output can also be taken across collector and emitter of BJT. Then output voltage equals to VCC minus voltage drop across this resistor, that is IC multiplied with RC. Here VCC is a direct voltage and cannot pass through this capacitor. Therefore, only varying voltage minus IC/RC will appear across output. The minus sign simply indicates the phase reversal. This method of taking output is used in multi-stages of amplification, while the first method of taking output from the collector load is used in only in single stage of amplification. The basic function of an amplifier is to raise the strength of an input signal. Gain of an amplifier is its ability to amplify the applied input signal. Gain can be calculated by the ratio of output to the input. Hence, the voltage gain of the amplifier is the ratio of change in output voltage to the change in input voltage. Likewise, the current gain of an amplifier is the ratio of change in output current to the change in input current. The three primary currents IB, IC and IE flows into a properly biased BJT. Here the direction of conventional current flow is like this. The base current IB and collector current IC flowing into the transistor and emitter current IB flowing out of the transistor. So by applying KCL we can write IE equals to IB plus IC. Here input signal is applied to the base terminal. So IB is the input current. Output is taken out from the collector terminal. So IC is the output current. So the current gain of the BJT is the ratio of output collector current IC to the input base current IB. It is represented with symbol beta. We can find beta value in manufacturer's data sheet. BJT's current gain often represented with BDC and BAC and also in terms of HFE. HFE with capital H used for DC gain, whereas HFE with small letter h is used for AC gain. Every BJT has its own unique HFE value. For most small signal BJTs, this may be in the range between 10 to 500. For example, HFE 100 determines if 1 milliampere of current fed into the base of the BJT, then the collector current will be 100 milliamperes. That's all about bipolar junction transistor. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.